all of those caveats aside, let me go get recording started here and get going. We left off before our demo day, and we were talking primarily um, at a very high level about the graphics pipeline and the various evolutions of OpenGL to kind of match the corresponding evolutions of the graphics pipeline. And this is one of the figures we left off on. Not all of the details are necessarily super critical here in terms of, do we need to know all about tessellation control and evaluation shaders? Probably it would be sufficient for us to say, as we look at the current modern OpenGL 4 pipeline, is that there are additional shaders beyond just vertex and beyond just fragment shading. In this case, these would be additional kind of geometry type shaders. Um, this is the 4.0-ish pipeline. We also had a version of kind of the state machine view of it. There's been additional features that's been added since 4.0, and we're at currently version 4.6. But in terms of pipeline stages, version 4 is kind of the current state of the art in terms of what is available for you as the programmer to interface with. Um, I think that was sufficient in terms of say that there's different versions of OpenGL. There are also other things in the so-called OpenGL, like class or family of APIs, that main kind of just plain OpenGL is effectively positioned as the workstation API. So like we are using it in class, that is how we are um, generally using OpenGL. You're sitting at a computer, you're developing for that particular workstation, and that is the class of API we're interfacing with. You may have also already seen the term or familiar with OpenGL ES. There, the ES stands for Embedded Systems, and it was effectively you could think of it as a fork or just a different target of OpenGL in terms of what features were being supported, designed for embedded or other handheld devices. Your cell phone is capable of doing OpenGL ES version 3 point something, presumably 3.2. It's a pretty stable version. It also is effectively the same as OpenGL 4 in terms of the functionality that's provided. Some of the API calls are different, but they're not different in any, I would say, interesting ways. And so our knowledge of OpenGL 4 for the workstation API maps directly to OpenGL ES. And so if you were to interview for a job with regards to OpenGL ES in some embedded scenario, you'd be fine. You'd be fine with your current background learned in this class to claim, well, I haven't actually touched OpenGL ES. The tool chain's different. The flow of compilers and things like that are different, but it's effectively the same graphics model and class of functions in the API. So you'd be quite capable of taking on that task. Um, WebGL is becoming increasingly more important because it's supported by all web browsers, so it's kind of a nice portable target for doing GL type of graphical rendering. Um, it can be run without recompilation across all different platforms that have modern browsers. It can also be integrated with other web applications. That makes it a very nice thing there. There also, it is extremely similar to OpenGL ES, modern OpenGL for workstation. There's different targets for it, but generally there's a JavaScript target for it. And if you were to look also at WebGL, you would see the same thing. You would see that it is very similar to what we are learning in this class. I would argue it's a little bit easier because you have to do a little bit less of the make file plumbing and things like that to be able to make sure you get a window up and running. You're running in a web browser. You have that kind of surrounding context already provided for you in a reasonably cross-platform manner. It's using JavaScript and not C and C variants. So that may be easier, maybe harder for you, depending on your perspective or background there. I think if this was a class entirely just on OpenGL and we weren't doing any of the kind of interfacing or design of the underlying hardware, WebGL would be a pretty good choice for that. I wouldn't have to change the slides any for the most part. It would really just be using that as an easier platform to get started. To get the first red triangle up and running is quite a bit easier in WebGL versus in just conventional workstation OpenGL. But otherwise, you're not really missing anything there, right? So we're learning the core concepts. You maybe get the corresponding book or web tutorial for WebGL, and you'll be just fine with that as well. It also allows for all sorts of really cool web-based demos. Well, I'll try to bring one up at the end of the day today. The main issue with some of those demos is they are incredible. Web browsers and corresponding laptops can't always keep up with those demos, so I don't want to click on that link right now because I may crash everything and then the recording will get all messed up. But at the very end, we can afford to do that, so I may give it a try at the very end of our class here. So as we actually start to talk about the mechanics of working in OpenGL, and I know for MP1, at least one person per team got a little bit of experience in doing that. I want us to be all on the same page at this point here. Let's start with a more simplified version or model of the OpenGL pipeline. We know there's other stuff than what is listed here, but for our purposes of understanding OpenGL, this is going to be sufficient. So generally speaking, in this simplified version of the OpenGL pipeline model, you have data that's going to flow through your application through the GPU to generate some image, right? So our end target is that frame buffer, as we've talked about. Your application's goal, the whole point of the OpenGL application, is to provide these vertices. And I do want to make sure we're using the terminology correct in this class, and maybe it's become clear to some and still needs more clarification for others. When I refer to a vertex or vertices, that is the collection of data. It's the group of data that is composed to form those geometric objects that software would then be specifying, copying that data over to the OpenGL pipeline. So when I refer to something as a vertex, we tend to think of it as being something that has a position. But that is just one of potentially many attributes associated with that vertex. So don't think of it as a vertex as a position, and then we can also specify color. Those are both just examples of attributes that taken together are what is referred to as the vertex. So I understand why it may make sense to keep it separate. We almost always have to specify like position information, so that's sort of a necessary or required attribute. But then it's just one of potentially many attributes associated with a vertex here. So it's not a separate thing. It's all combined together in our application that we're writing into OpenGL. We may allocate the memory for that in different buffers and do some of the plumbing slightly differently, but they're all corresponding to the same thing, which is the vertex. So our application specifies this data, this collections of data to form these geometric objects, these vertices that we have here. There is then that vertex processing stage that uses some sort of vertex shader, some sort of programmable piece of software running resident on the GPU to do any sort of computations corresponding to that vertex to determine ultimately a relative location in the scene for where that geometry we're specifying should go. There's other shading stages are potentially there as well. Your tessellation, your geometry shading, those are also used effectively for vertex processing. But keeping this simple, we can think of this as just a single stage where vertices are specified. We then have this shader that is doing this processing of those vertices to get onto the next stage. After all the vertices for a particular piece of geometry are specified and processed, there's then this next stage, that rasterizer stage. Talk about the definition of a raster scan or a raster image. The term comes from this concept of we're going line by line. This may be backwards on your screen, but we're going line by line and we're processing the geometric object on a line by line basis. It's a piece of hardware. It's the piece of hardware you're working on hopefully right now in your labs this week that determines which pixels in the frame buffer should be affected by that geometry that's specified. So for MP1, we didn't have to worry about that stage. We specified everything as a point, and it was a little bit of a hack. We were specifying all of our geometry as just these individual points in space, and so we could assume that there was a one-to-one connection, that for every vertex we specified, that was going to correspond to a single fragment there. That is technically kind of a pass-through rasterizer. So we take the vertex, we do nothing with it. We just then decide to call it a fragment magically, and then we connect that to our render output stage. Now, as we're specifying other things, lines or triangles or other primitive types, there's that intermediate stage that we are collecting the requisite number of those vertices first. We combine them together and then treat them as one geometric object. Just think of it as a triangle, and I think you're fine here. And now there's this stage that then takes that triangle and determines inside that triangle what fragments should be affected in the frame buffer based on the parameters of that particular triangle here. After we've done that, The output of that rasterization is one or multiple fragments. Those are the potential pixels, right? So for each of those that are generated, there is another programmable stage that's our so-called fragment processing. We can do all sorts of things in that stage. We can do lighting calculations, we can do texture mapping, we can decide that we just don't want this fragment, we want to drop this particular fragment. But the end result then is going to be something that's going to be output to our frame buffer at the end of the day. So this kind of left to right flow on my screen here is a good enough simplification that I think we can use this to kind of influence our understanding of OpenGL, because then we have to just for every one of our applications in OpenGL, we really have the same number of tasks that we have to do, uh, kind of independent of the complexity of the scene itself. For our scene, we have to specify what are our vertices. So a lot of our OpenGL code is determining what is our geometry and what are our vertices and what attributes do they need to have. We also, although I try to hide some of this details in the API that we're using, the little middleware library that we're using, we also have to specify and load our vertex and fragment shaders. And of course, if we're using any other shaders, we have to specify them as well. We then have to have a step that just issues the geometry that says, okay, we've allocated memory, we've determined what our vertices are supposed to be. Now issue that subset or entire set of vertices and tell the GPU effectively to get going. Yeah, thanks, man. A fragment is a potential pixel. That's the sufficient definition for now. Um, the idea being, and we had that one real simplified pipeline graphics pipeline, and that's probably the easiest way to describe it. Although we have other examples here, a pixel is something that is on your screen. That is meant to be a sample in that two-dimensional space of what you're trying to render, right? That is a pixel. That corresponds to what is actually on the display hardware at the end of the day. The output of our rasterization is a potential pixel. Although here it shows there is no potential, it kind of shows that direct connection from fragment processing to output. But we've specified a triangle, we've rasterized the triangle, we have a set of red fragments, potential pixels associated with that red triangle we have here. And we may or may not actually want that red triangle to be on the screen in that location at the end of the day. Perhaps it's behind something else. Perhaps there was a blue triangle in front of it, or perhaps partially it's being blocked by some other geometry in the scene. So that's why we kind of differentiate the two. One is potentially going to be a pixel, and then finally our render output or some other final stage is going to have to help us determine, okay, is it actually going to be something we finally put on our screen or not? For now, they're effectively one and the same for our purposes, because we're not checking any of that as of yet. We're keeping everything two-dimensional, in which we specify a fragment, it's going to get put on the screen. But pretty soon we're going to relax that assumption just a little bit at least. In terms of our OpenGL programming skill set, there's no shortcut to trying it out and doing it yourself. I think what you will find is that a few basic techniques will go a very long way in terms of at least not limiting your creativity with what you want to be able to do with OpenGL. In fact, most OpenGL programs, in terms of what they're doing from an OpenGL perspective, are very repetitive. I hesitant to say boring, maybe the right word would be sort of like mechanical in nature in terms of how we interface with OpenGL. The main differences usually occur on the more creative side in terms of what object we're going to have and how they're going to be rendered. In terms of the creativity, in terms of how we process vertices and fragments, that's still in OpenGL, but that's more on the shader side of OpenGL than in this API call side of OpenGL. So we generally are going to have the same four steps over and over again in any OpenGL program you're going to see. You're going to first load and create your OpenGL shader programs, and by spec, it has to at least have that vertex shader and that fragment shader. Next, you're just going to load the data or generate it however you need to for your objects that are going to go into OpenGL's memory. So as you hear and read the term buffer objects, that's what we're going to be talking about here. You're going to create these buffer objects. You're going to be loading data into these buffer objects. You then also have to kind of connect the shaders to your buffers. This part's a little bit subtle, I would say, but one way to think about it is that OpenGL needs to have a mechanism and in your hardware needs to have some mechanism that by which we can associate. You can think of them as input variable names in my shader code with these buffers that I'm generating in my OpenGL C code or C++ or whatever code you're using here. So it's like a shader plumbing kind of stage where it can be done with fewer lines of code, but a little bit harder to read. Or you can be very precise in it and say, I'm looking for this attribute name in my shader. I'm going to correspond to this buffer I have in my code, and that's how it knows that color information is going to correspond to this buffer that you've generated in your code. So you have to create your shaders, initialize your data, connect your shaders to your data, and then there's just that final step where you say, go. You have your data initialized, you have your shader set up, and you're saying, okay, now render your objects at that step. The other caveat, although I think now that we've been using it already a little bit in lab, is not it's not that big of a deal for us. You know, OpenGL is the one that's gonna, as you specify things, will take care of filling the pixels in the output window. But it actually OpenGL itself has no direct defined mechanism for creating that so-called rendering surface. So OpenGL itself doesn't have API calls to generate a window, to create a window and to do things like handle click events, mouse events, and keyboard events and things like that. So sometimes part of the headache and or extra difficulty of working with OpenGL is directly due to that fact, where you're really dealing with at least two libraries every time you have an OpenGL program. So you'll have a library to do the stuff that we're talking about right now. Create initialize buffers, associate buffers with shaders and things like that. And then you have to use some other library to then take that rendering context and then bind it to the underlying windowing system. And that can be okay, and that can be a pain depending on which one you are using. That also leads to some challenges with sort of compatibility between different OpenGL programs out there, because the OpenGL code itself is very portable and well-defined spec. But then the underlying windowing code that this particular example you may be looking at may be quite different than the one that you are using yourself. Um, we are using that GLFW, Graphics Library Framework. It's a well documented, it's a reasonably good multi platform library, and that is what we're handling all the windowing operations for us. Not to put too fine a point on it, there's a little bit of a chicken and egg thing here. So we have this GLFW library, and it's going to have functions like create window, which is the kind of thing that seems like naturally we would need to have. Create a window, give it this title, make it this particular resolution. Under the hood of GLFW, if we were to look at the implementation of GLFW, it is also calling OpenGL calls. I mean, what does it mean to create a window? Well, we need to render a little title bar, and we have to have some widget to do a little X in the upper right-hand corner so that we can close out of it. We have to render fonts for the title of it so that it looks reasonably readable in our underlying system. So GLFW, depending on how it's created and where it's being ported from, is going to also do a lot of OpenGL calls underneath the hood, either directly in the GLFW implementation or indirectly via interfacing with whatever the native windowing system. If it's a Linux system, it's likely also to be using OpenGL. So there's a little bit of chicken and egg there, not to belabor the point too much, but as we have our lab infrastructure and we are capturing and potentially processing every OpenGL call that we receive in the application, we explicitly have to tell that capturing mechanism, hey, capture all the OpenGL calls, but make sure to ignore all the ones from our windowing system, because we can't implement those yet. Those are more advanced. Getting a nice looking window is more complicated than rendering just a single triangle. So there's a little bit of a chicken and egg there. Other graphics APIs don't deal with this at all, don't have this particular challenge at all, for better or for worse. If this was a class based on DirectX, Direct3D, and all the other direct family of graphics and related libraries for Microsoft, our life would be simpler in that sense. We would be learning one kind of defined framework that handles more than just rendering. It's the same framework for doing compute as well, same framework for doing windowing, same rendering for handling audio and all those things of that nature. The flip side is there's a lot more code you wind up writing for the equivalent kind of examples there, but it's all one given framework here. With OpenGL, for better or for worse, as kind of a primary design decision, and perhaps given its genesis in a world in which there was a pretty big disconnect between different manufacturers and software manufacturers and the libraries and windowing approaches that they took, OpenGL is completely disconnected from that. So you always need usually though at least those two things: OpenGL, whatever version your system is supporting, plus some windowing framework so that you can actually get a window up and running in a particular system. I think I kind of mentioned that, so operating systems have different ways of doing windowing, for example. There's a slightly different consideration as well that given all the different capabilities of OpenGL, given all the different versions that are potentially supported here, and I think that's the bigger of the two issues there. Given all the different versions, each of which has different compatibility profiles, can support a different subset of OpenGL, um, and then some hardware manufacturers can support things in addition to what is kind of the conventional core profile of OpenGL. Um, there's actually tends to have to be a lot of management of that at the very beginning of your application. You effectively have to determine um, in an OS specific manner, so the Windows approach would be actually be quite a bit different than Linux, would be different than Mac as well. You'd have to determine what functions can I actually support. So I'm writing this OpenGL code. You effectively have to do some version querying at startup and say, I want to use this particular function. Can I? I want to use this next particular function. Can I? If we were to write our OpenGL codes ourselves to do all that kind of querying ourselves, of checking for compatibility, that would potentially be, a very just big distracting thing. That'd be pages of code where we're just kind of checking for that particular system, what library is supported, what version is supported, what API calls are we expected to be supported. So while I mentioned there's always generally a second piece here, so here's your core OpenGL API that we're interfacing with. Here is whatever windowing API, that's our GLFW. You may see a lot of examples online using Glut, which is it's fine, but it's a little dated for windowing, and there's many other solutions as well. We also tend to also interface with a third library separate from OpenGL to deal with the potential compatibility and different extensions that may be available on the particular hardware and driver that you are using. The one we're using is called Glue, OpenGL Extension Wrangler Library. And the nice thing about it, as we look at some of the source code examples for today, it's effectively one line for us. That one line is doing quite a bit of work for us, but that's what that one line is. It is basically query all the potential compatibility modes and extensions that are available on this particular system and return back a reasonable good compatibility with the list of possible functions here. That simplifies compilation, that simplifies linking, and at runtime, that provides some guarantee or at least a graceful exit uh, that we have the functions that we are expecting for those. So this is why people don't love OpenGL necessarily. It's not OpenGL itself. It's all the other things that tend to have to go into it to provide a working Hello World solution or Hello Red Triangle solution. Once you have that, though, um, I don't think there's any point in being strongly opinionated about the value of this set of API calls versus some other, competing different set of API calls. It's all pretty similar to each other in terms of the mental model of what's happening in the pipeline and how we're interfacing with it and what we're specifying and how we're querying for status and for results as well. I guess my goal with describing that and talking about that is to kind of make sure that when you look at these examples, there's parts where I'm basically specifying, hey, don't worry about this too much, right? But you should at least be not ignorant of what's happening in those parts here. So every line of code in those examples that we provide for MPs and in other contexts are valid and necessary, and this should give you the right background to at least as you're copying and pasting that into a new example to kind of demo off different functionality. At least then gives you the right context to say, yeah, that's why this piece of code is here. This is why I'm copying, pasting it. We oftentimes don't have to change any of that. But now, if you were going to work on a totally different system, separate from this course, you at least would know where to start in terms of how you would do that kind of porting of code over from one system to another. But I am well aware of kind of, you can call it the irony, you can call it what you want with regards to working with OpenGL. The whole idea is it's cross platform, it's compatible with everything, it works on everything is a lot less true now than it used to be. Um, if you truly want write once and run almost everywhere, at least on conventional, desktop and laptop computers, then WebGL is probably the way to go right now, and it's not this so-called very portable cross-platform OpenGL. Let's talk geometric objects. So this is would be true in all other graphics libraries as well as within OpenGL. We have objects in a scene and they're composed of these geometric primitives, which themselves, the geometric primitives are described by vertices. A vertex in modern OpenGL is just a collection of data values associated with a location in space. Those other data values could represent things like, I already mentioned, color, some like normals or other reflection information needed for lighting, maybe additional coordinates that don't correspond to a three-dimensional space but correspond to the texture coordinates used for texture mapping. Locations can be specified in either 2, 3, or 4 dimensions, but internally, in terms of at least the drivers and the hardware's representation of the position, it's going to be in these 4-dimensional homogeneous coordinate system. So we will see that depending on how we specify things in OpenGL, we may specify that all of our vertices just have an XY location. They're a 2 vector. Or it may be very important for us to specify it as an XYZ location. It's a 3 vector. Less commonly in terms of specifying, we may want to use that 4th dimension that we'll be talking about here. So then it would be a 4 vector in that case. But one of the first things that then happens, though, is no matter how we're specifying our positional coordinates here, it's going to get converted to this homogeneous coordinate system where everything is going to be that 4 wide vector for those purposes. On the workstation side or application side, our vertices get organized into these objects called vertex buffer objects. Just call them VBOs is fine. And that's what you need to set up in your application. That's what contains all that vertex information for all of the primitives that you want to draw at any one given time. VBOs can store vertex information in all sorts of different ways. You can have an array of structures, each containing a single vertices information or single vertex information. You can also have a structure of arrays where all the same type of data for a vertex is stored in a contiguous array. Another way to think about that is you can interleave position, color, texture, position, color, texture, or you can do position, 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 color, 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 texture, texture, texture. The calls to the buffer copying just have slightly different parameters depending on how you are doing that. Either one is going to be fine. From our perspective, how we wind up organizing things in memory, we do want all the vertex attributes to be in a kind of consistent layout so that when we have that vertex fetch module that's already kind of baked into the hardware, it's not terribly clever. So it's looking for 4 attributes at a time and it's loading those all from specified locations in memory. That limits a little bit of our flexibility, but in general in OpenGL you have a lot more flexibility than that in how you're specifying your input vertices. That's our VBO. That's the data that is needed to represent the vertices for all the primitives you want to render at any given time. These VBOs then, and this is more of a like a metadata type of format needed to kind of keep track of different things that may be happening in your scene. Your VBOs are then further required to be stored in what's referred to as a vertex array object or a VAO. It could be the case that you would have numerous VBOs associated with a single object. So your VAOs are there to kind of simplify that management of your collection of vertex buffer objects. For us, at least in practice, all of that aspect of kind of keeping track of what buffers are associated with what VAOs, that's all being handled entirely driver's side. And likewise, if your scene isn't terribly dynamic, things can be moving around, you can be changing your geometry, but if it's not a fundamental change from one scene to a next scene, we can have a pretty close 1-to-1 correlation between VAO and VBO. We can have a single VAO for our program generally, and one or multiple VBOs then associated with that VAO. That's all a little abstract, but I'll show you what that looks like in practice. In more complex scenes, you may want to be rendering with a lot of dynamic things and things coming in and out of the scene. There may be some value in having multiple VAOs then, and then you're switching between them. It's kind of like switching state of the application or switching state of what data the driver needs to be aware of and care about, and likewise what data needs to be either read or written to the GPU at the end of the day. It's referring to this 4th dimension that is not necessarily corresponding to anything directly in a 3-dimensional space, but is also just more of like a mathematical trick to allow us to specify all sorts of what would otherwise be nonlinear transformations in a three-dimensional space, still using kind of linear algebra to represent those transformations. Another way, that's the mathematical answer. The other term you may hear it referred to as the perspective of a particular object. Um, in a single vertex in isolation, W doesn't really mean anything, and we can keep it as a value of 1.0. As part of a more complex series of transformations we may want to apply, we may wind up with a vertex that will have a W value of not equal to 1.0. If we want to apply certain transformations, we then will have to have a separate step in hardware that takes that W value and then normalizes it. So that's not a great answer, but that's why it's there. It allows us to do more complex 3D things while still staying nice and linear in terms of the math required here. And then that has implications for hardware as we will see. So that's not an off-topic question. It's also not a question that it'll take us a couple weeks and we'll have a, I don't know if I would call it a satisfying answer, but a reasonably factually correct answer for why we have that W parameter there. Why are we wasting our time specifying it and passing it down the pipeline when it's almost never changing for anything that we're playing around with in this class? That is the case until it's not relatively late with some of the transformations that we will be learning here along the way. So this next part you've already started to explore, I think, with regards to your MP2 hardware that you are building. So to form these 3D geometric objects, you need to decompose them into primitives that OpenGL itself is aware of. Generally, OpenGL and the underlying hardware knows how to draw three things. This is for that simplified pipeline view, at least. It can draw points, it can draw lines, and can draw triangles. Then, if you need anything more complicated, you would use collections of those to draw something more complicated than an individual point, line, or triangle. So you have those types listed there. We could spend a lot of time and build hardware for line strips and line loops. It's very doable. I just thought for MP2, there's enough work to just focus on triangles that we really look at triangles, triangle strips, and triangle fans. I think next week we'll talk a little bit more about primitive assembly for both those last two cases. That's a good use of our time. You have to build it in hardware. We'll spend a little time in class talking about that as well. Always a bit of a risk when I'll say googling examples of OpenGL. This is true of a lot of things in life. I think you have to be careful, but with OpenGL, it's very much the case that you have to look at like, okay, here's an example that seems really great, that seems to really explain what's going on. You always have to be very aware. Okay, what version of OpenGL is this corresponding to? Sometimes it's obvious, and the developer and/or person providing an example makes it perfectly clear. Other times, it's less obvious. For example, you will find online all sorts of examples of OpenGL code that uses different primitive types than what's listed here. GL polygon or GL quads, etc. Those are all deprecated. And generally, though, you can replace that code with a GL triangle fan. Given this fan of triangles where you're specifying that first point and then successive pairs of points to build up a more complicated polygon shape, you can build a lot of stuff out of that. But just a small word of warning about that as you look at examples online, they're not always that obvious. What version is this based on? Usually, you can do a porting from one version to our more modern supported version that we're using in class, but it's not necessarily trivial. It does take a little bit of effort along the way. So here is going to be our primary example, and I think by and large, the example that you'll be spending the most time with in lab as well. This is the simple red triangle. The idea and the point of this example is to keep it as straightforward as possible and just use it to illustrate the things I was talking about, the shader loading, the shader plumbing, right, the associating buffers with the shader attributes, the vertex array objects, the vertex buffer objects, and then the actual kind of draw call that is happening here. Whether or not you can see the code as I open it up here and whether it's going to look super legible to you or not, this is just example from MP2 code. So As you're following along live, I can certainly make the font a little bit bigger, but definitely just look at the examples from MP2. Likewise, you can also run those examples if you want to see the result. The result isn't that interesting; it's just a red triangle at the end of the day. But just to remind us of what we have for that example, we're specifying three vertices here to correspond to a triangle. We then um, that triangle does not look particularly red. Let's take a look at the code here. Those attributes look reasonably red to me. Always very common to lose time while we're working on things by not compiling and checking the most recent version of stuff. Okay, no, there is our red triangle here. Um, in terms of testing your hardware, um, in class, in lab, where you're either simulating a triangle or you're trying to capture data on the ILA or you're trying to manually debug what you're seeing on the screen. This is probably where the vast majority of your time needs to be spent. There's a few caveats with regards to that, and so those of you who are half with me today, this is what I want you to remember out of today in terms of how it corresponds to the lab. This is a really good test case because it's a triangle and it's a perfectly valid triangle. It's a pretty large triangle. You can learn a lot and test a lot by just making a smaller version of this triangle. As we'll see as we look at the syntax, this is our x, y, and we're specifying z even though it's all zeros. You will be in reasonable shape specifying instead of, a good chunk of our normalized positional space if you instead just specify um, a smaller amount. There is no like exact smallest amount that would be appropriate. But if you're spending lots and lots of cycles like looking at all these huge simulation streams, because each of those you'd have to simulate along the way, each of those fragments, to confirm that your rasterizer is working as intended, um, just make it smaller and test that. And then, there's less things you're looking for, less data you're looking for. That's one thing to consider, that you spend a lot of time on this triangle. However, there are lots of bugs that occur that you will not realize that you have if you are only testing one triangle. So there are other applications that are not accidentally selected for you to look at to consider renders that are multiple triangles. Snowflake is one I would actually suggest skipping until you're relatively close to 100% done. It does not look bad. It is Coke algorithm that kind of generates subdivided triangles to give you a kind of nice snowflake pattern here. It's hard to look at it. Certainly, if you're looking at my screen or in Zoom here, you're not seeing it super well. Those are very tiny triangles. So there's some value in large triangles, but you need really small triangles for this one. And that may be exposing some bugs in your implementation of the rasterizer as well. You may be making certain assumptions about, well, the triangle will never be just one row high. We always have to go to look at the next row. That may not be the case for some of these triangles here. So this is a good, I would call it a stress test though, because it's testing both lots of triangles and maybe more than it looks like at first blush here. And they're really tiny triangles. So that's a good one to have, but don't get terribly discouraged if it's not working for you, certainly on your first or second try. I like RAN triangles to some extent. Certainly, if you want to test two triangles versus just a single triangle in what you are doing here, this is a decent one. You could think of it as a stress test in terms of it's a lot of triangles it's generating. The downside of this one is it's too many triangles. If you were messing up one of these 100 triangles here, you're not going to be able to visually inspect and see if that's the case. Okay, if your application hangs, if the hardware kind of gets stuck, then that's a useful test. But you're not going to be able to look at every single pixel of this and know certainly that it's the case. One way you could change this application, it's generating n random triangles where n is reasonably large. Change n to 2, and then change n to 3, and then change n to 4, and test it that way. That gives you a finite number of triangles, but more than one, so you're at least testing different characteristics of the triangle. You may not believe me until you try it yourself, but there's a whole class of bugs that happen when you make the assumption in your rasterization and your traversal algorithm that it's this nice, well-formed equilateral or other kind of triangle, like a very you know, boring looking triangle shape. Once you start to have really thin, really wide, really obtuse, really acute, angles in your triangles, some of the things that made perfect sense um, will require you just to test those edge cases in your state machine, where the red triangle may not be testing any of those edge cases because it just follows such a nice predictable pattern in it. Take it one by one. When you find a triangle that breaks your implementation, that's a good thing. You have this data point that you can now use and you can build a test bench for it, right? And you can really figure out, why am I getting stuck or why is it not working here? But don't just try to run this whole application and treat it as a binary result. Yes, it worked. No, it failed. I mean, that's useful, but you need to do more than that, I think, right? And you need to figure out the why questions. And your best bet there is, I think, to kind of try to isolate the problematic triangles for you. This one is color wheel. Um, this one, actually, even if your um, rasterization is done, may not look good because it's going to expose a bug or a limitation in your render output implementation in terms of how it's handling colors. So this is just kind of a basic color picker kind of application. It's composed of a couple different triangle strips, including a little tiny one being used for this little circle, which you may not be able to see, this little circular highlight here, and then a single triangle for the center. The one I would argue is probably the best once you have red triangle working. I wouldn't start until with any of these others until you have red triangle working. Is this triangle kind of paint application? Doesn't look like much at first usage, but it allows you, as you're interfacing with hardware, to just without having to recompile your application. You can always change the red triangle.cpp and change which triangle you are sending here. This one allows you just to use your either left or right mouse and kind of just grab the vertices themselves and change which triangle is being specified here. And that allows you to understand things like, well, my triangle works great until I actually have it upside down, and then it doesn't work very well anymore. Or, something is clearly wrong when I have a super sharp triangle like this and my hardware goes haywire. Each of these can then effectively generate a separate test case for you to use in simulation to see what may be happening here. That's when you left click on a vertex, allows you to drag and move it around. If you right click on a vertex and then kind of drag and move it around, you can just specify different color gradients there. I think for most of your implementations, you'll be okay with color. Once you get X, Y, and Z working, um, the other attributes should also just kind of work. It's very formulaic in terms of your hardware implementation at that point. But this is one way. If something happens to be wrong with your blue channel, you can create test benches through this that would allow you to specify the exact triangle your hardware needs to be able to expose one particular bug. You can take the output of what triangle got generated here, connect that to some sort of axis stream test bench for your either primitive assembly or, in more likely, your rasterization core that you have there, and then you can test that versus this kind of binary, it all works or it all doesn't work kind of scenario, where for MP2 specifically, the design cycles are pretty long in terms of small changes. You have to wait a little while to get a result back out. You want to be very intentional with your testing, your debugging strategy, and this application is a pretty useful one for that. So that's some of the MP2 applications. The one I want us to focus on the most, starting right now, is the red triangle one. So let's spend a decent amount of time on what is otherwise a relatively straightforward OpenGL application here. So we have these VAOs, right? That's going to store the data of the geometric object, our vertex array objects. We have to do what OpenGL refers to as generating names. You can think of it as generating IDs. I think it's not a named object in a meaningful sense, but you generate those names by calling GL gen vertex arrays. You then are going to bind a specific VAO by calling GL bind vertex array. You're going to then create and update the VBOs to associate with the VAO. And then when it comes time to actually rendering, you're going to specify which VAO you're going to use for that particular rendering. This at least gives you the ability to say, I have a whole bunch of different vertex buffers that I'm using for different purposes. I'm associating them with different VAOs. When it comes time to do this rendering call, I want all that objects corresponding to this particular set of buffers associated with this VAO, and I'm just going to have a single call that allows me kind of to change that context of my render. So it is a nice feature, but if we're just doing a red triangle, it does look like kind of unnecessary work here. Let's take a look at the source code for the red triangle. Let me actually just even start, in the beginning of the couple things we mentioned here. So we are using OpenGL stuff, but in addition, we're also using that glue extension wrangler and GLFW for the windowing itself. So first thing first, we actually want to make sure we can actually create a window that we're on a system that can handle OpenGL in the first place. It's a nice kind of, early error checking, but we specify a particular window we're interested in. We don't have to limit ourselves to 1280 by 1024 windows. There are sometimes some gotchas with regards to resolution. I talked about that a little bit in the demo day on Tuesday. Um, we have this output monitor. Our output render, at least resolution, is 1920 by 1080, the 1080p resolution. If we were to specify a window of that size, which our workstation can certainly handle, part of that window is going to be set aside for like the actual windowing stuff itself, the little border around it, the little title bar at the top, the little buttons to exit or minimize or maximize. We don't actually wind up with an exactly that sized OpenGL context at the end of the day. And unfortunately, the actual amount of pixels in our OpenGL context is really system dependent. If you're at different resolution, scaling, different operating system, different windowing manager that you're running in the operating system, you'll get slightly different results there. We're pretty safe in specifying this sized window, even knowing that we're not technically filling the entire display with pixels when we do this. Gives us enough wiggle room that everything should look pretty good here. These next two lines of code, after we've done the GLFW, is hiding a lot of the complexity of determining what API calls are going to be able to be supported on this particular system. Your code will not work if you don't have those two lines there. I think from our perspective, it's sufficient to say, excuse me, it's sufficient to say that we need to have that. That is handling all the library kind of handshaking for us to determine, okay, for this particular system, things are going to work just fine for us. We are just doing some more GLFW calls to be able to handle the escape key that's necessary there. We saw this already in MP1 that there's a call to GL clear. GL clear allows us to clear different buffers in the system. The primary use case for us, at least this semester, is to use it to clear as like a background color, to clear and to specify whether we want a light blue background behind all the other stuff that we are doing here. In this case, it's a dark blue background that we're specifying. For better or for worse, this is a very inefficient call for us in OpenGL with our hardware implementation. There may have been some better mechanisms to get this to work, but the way I have implemented this with our driver and with our underlying hardware is that when we specify GL clear color, we're actually copying a whole frame-sized buffer of that number of pixels. There should be a better way. We should be able to do some clever DMA calls so that we only have to store like one pixel versus storing the whole frame. But that's basically what what is happening here. That is basically drawing or specifying an amount of memory saying, give me that many dark blue pixels in memory. So when I actually call GL clear, that's a DMA operation. That is copy from this clear buffer to my frame buffer. That one's about as efficient as you could expect, I think, it to be. But that clear color call becomes the slow one then because the driver is now saying, hey, we have a new color. Let's update every location in memory manually, effectively, via that color. We could probably make it faster, but it's not. And that's why it's called Clear Test is one of the MP1 applications. It's always a good sanity check to make sure that like your stuff is hooked up properly, if nothing else, like the Ethernet cable is hooked up properly. That's why that's a very slow application. Every time you hit the space bar, it randomizes a new clear color, and that call is the one that's slow, not the actual call to GL clear. So that is a pretty common kind of set of background things to do. We didn't need to call this yet. We could have moved it quite a bit later, and this code would be fine. And now we have our vertex array object, what do you want to call it, bookkeeping code here. where we're going to generate the names or generate an ID calling gen vertex arrays. We're going to then bind and say, here's our current one that we're currently interested in by calling GL bind vertex array. And then if later we need to use a different one, we would then call GL bind vertex array um, at some point again in the future. So we have, and this is also one of the not great things about OpenGL is its kind of lack of real object-oriented nature to it. We are specifying just as really as an integer handle. And that's what this is here. Particular vertex array ID. That's just our variable name in C. We are then saying we want to initialize, in this case, just a single vertex array object in our program. You may want to have multiple, but our code's going to look like this a lot, where we just have the single VAO, so we can initialize it by reference there. We could also have specified, we wanted 50 different ones, and you would just pass that and pass 50 for the number of VAOs we're initializing here. And then we're also saying for that particular ID, that is the one that's current. That's what all of our next calls are going to then be associated with, that current vertex array object. Necessary code. For our purposes, copying and pasting that, having the beginning of your programs is probably going to be okay. Next up, we have helper functions. This is not an OpenGL call. There's no call called load shaders that deals with the mechanics of basically allocating the text for our shader programs, compiling that text, linking that text, basically making an executable shader program to run resident on our GPU. We will talk more about that as we become more expert on the shading side of things. But for now, that's what's happening there. We do need that in every particular program. Those are the so-called pass-through shaders that we talked a little bit about in class last week. They're called pass-through because they're really not doing anything very interesting. We messed around with them a little bit, but we can mess around with them more for the red. But for now, at least, pass-through shader is just taking an input attribute of vec3 called position, taking a separate input vec3 called color, and it's providing two output values that are the output of that vertex shader. So it is doing, you could argue it's doing a little bit of like concatenation or something. Take our XYZ and concatenate 1.0 with it. Take our RGB and concatenate 0.0 with it, and specify kind of always as a given the default. And there's different ways and different versions you would see this. Specify the default output position, specify an other user specified output color, and just pass that data through. Likewise, on the fragment side, it's doing something very similar. Here, we don't care as much about position, although we can specify that as an input if need be. But for now, we're just making sure for that fragment that got generated, here is the output color associated with that fragment. So the actual vertex data, I've been saying VBO a few times. I haven't really talked about how one goes into actually creating them. So vertex buffer objects are just another type of memory object. You can think of it as just an array, although it can be some sort of packed structure of arrays or array of structures. But it is otherwise just what we are associating with the attributes in a particular set of primitives for a part of our render here. So same kind of sequence of calls to what we did with the VAO. We first have to generate VBO names, and here we will certainly have more than one VBO for our particular render. You have to generate that buffer's name by calling glgen buffers. You then have to associate something and say, this is my current VBO that I'm interested in. That's called, the call to that is called GL bind buffer. There's going to be different types of buffer objects, so we have to specify what type it's going to be. In this case, and I think for all the cases for our purposes this semester, we're going to specify that we're going to have GL array buffer. So these are going to be buffer objects associated with our rendering process, and they're going to be corresponding to arrays of data in our program. We then actually have to load data into that VBO object. That's the call to GL buffer data. This is one of those examples in which there's like 30 different ways that OpenGL allows you to initialize data into a buffer. This is the only one that's going to work for us in our hardware. Now, a lot of that logic is all driver space logic. So you'll see a call. I even provide an example of GL buffer sub data on the next slide here. That one's also fine. It makes sense because it allows you to kind of copy into one big array multiple different attributes as part of a sub buffer into that one large array. We could use that. You would have to be the one to implement that call, is all on the driver's side to make sure data gets onto the GPU in the way that our vertex fetch would expect it to. There's nothing fundamentally limiting us from supporting those other buffer initialization and copying calls, just limited by time and I guess resources to be able to support those. So we have to generate a buffer's name. We have to make a particular buffer current, that's GL bind buffer. At some point, when we have data that is relevant for us, we have to call GL buffer data to copy the actual data over. Although, again, you look at the OpenGL spec, it's not that clear when the data needs to be copied over. For our purposes, when we have the GL buffer data, we know we can copy things over. And then finally, when it comes time to actually render using that data in the buffer, you have to make sure you're in the current VBO that's current, and then you can then say, okay, draw using the current buffers that we have copied over. This is a high level view of what that sequence of calls would look like. You generate a buffer, you make the buffer active, you copy data over into it. These are two different ways of copying things over. This is kind of like, you can think of it kind of like a GPU malloc type of call. The main difference is the underlying implementation is not really specified that clearly. It's up to us as both the driver and the hardware implementers to determine how that copy is happening. But we would then be specifying we are expecting to have this much amount of bytes of data resident on the GPU, and then we're copying that data over from the application buffers, whatever we've malloced or allocated statically in our application, over to the GPU at that point. That allows you to replace either the entire array, depending on how you call it, or replace some subsection of the particular array that we have here. It depends on the application, whether we are going to be doing just this once per buffer or whether we may want to do it multiple times per buffer. In this case, so we have load shaders. These now are our user application buffers that we ourselves are creating. Create them however you need to, right, for your application. In this case, it is now a small red triangle. We can go back to the larger red triangle we had before, and we've decided that we're going to have this static array for position information and a separate static array, in this case RGB, for color information here. And now we have the VBO kind of plumbing code corresponding to it. We have to have a name. So in this case, again, a name is like an ID. It's then also a variable name or an array of variables in our C code here. We generate the buffer corresponding to that name. We then make it current, meaning this is the current buffer we're currently operating on. We then are specifying that for this particular buffer, here's the data that we are going to have corresponding to it. It's of this type. Here's however many bytes we're going to be copying over. We're copying it over from this array, and this is just the name of the array up here in our application. And this is the nature of it. It's going to be for what it's going to be statically drawn in our particular scene. We're doing that for our vertex. We're also then going to do that for our color buffer here. And again, the OpenGL spec doesn't really say you must be copying data over at this particular point. But from our perspective, that's a reasonably good time at the driver to realize that, okay, you specify that you need this much data in memory. You've also then specified that you're going to have to copy this over at some point. We might as well copy data over at that particular point here. What we still haven't yet done, though, in sort of preparing that data for processing and sending it down the pipeline here, is we still have to say, okay, I have this shader code that has a set of variables in the shader code, the so-called attribute names in our shader code. I have these arbitrarily created buffers in my OpenGL code that I'm binding to these VBOs and collecting together into VAO. I still have to associate the two with each other. Seems kind of superfluous, but there otherwise is no mechanism by which we know that, even though I happen to call that vertex buffer object, what did I call it? position data or something like that, or color data. There's no way it has any mechanism of knowing that that actually is going to correspond to that particular named attribute in the shader itself. The extra complexity there is brought on by our own implementation, where we have it very fixed, where we are specifying, because of the simplicity of our vertex fetch module. This was in the MP2 video. If you took a look at that, that position is always attribute 0 for us. That's not an OpenGL requirement. That's a CPRE 480/580 requirement. Likewise, color is always going to be the very next attribute. There's no requirement we pass any color information at all in OpenGL, but that's our requirement. That's how we are going to do our rendering to make it somewhat manageable for the hardware that we're providing there. But in general, even if we know that it's going to be fixed for a valid OpenGL program, we have to make that connection. We have to specify for each of the in variables in our vertex shader, we have to specify what buffer object does that then correspond to in our program here. Let's take a look at what that looks like in our red triangle example here. And I would argue that this code is a little wrong in some sense, but I'll show you what's happening here. So for the vertex attribute array of 0, we're specifying now for the current VAO object. This is the buffer we're interested in. We are going to then, because it's the current buffer, associate it with it, and it's not that clear looking at the syntax at all here. Associate that with location 0 in our shader. Not just associate it with location 0 in our shader, let it be known that these are 3 wide vectors of floats, and they're not normalized floats. And it's starting at offset 0 of our vertex buffer object here. For the second attribute, we do the second thing. For the different buffer we have here for our color buffer, specify that that's going to correspond to attribute 1 in our shader. Those are also a 3 float, and it's not going to be normalized. If instead of XYZ we realized we only needed XY, you'd probably want to change the size of this buffer statically. You would also then specify it's only a vector 2 that we're requiring for that particular shader here. Let's take a look at the shader again. We specify explicitly in this version of GL slang that layout attribute 0, this is our limitation. We really need to be explicit with where we're putting things. Location 0 is going to be a vec3 called position. Position 1 in our layout is going to be a vec3 called color. That called here is what then corresponds and connects the buffer that we're interested in, the 2 buffers, with those corresponding fields in my input attributes of my vertices that I'm specifying here in my OpenGL. The reason I say that this code is not really tremendous in that sense is unless we're doing something really, I would say, funky here in which we're changing which buffer is going to correspond to which attribute, I would only do that once. So okay, there's no harm, but it's really for our implementation. Only at this point do we know. Okay, you have this big buffer of data that you specified. It's not that large here, but it could become quite large for some of those examples, right? Now I know exactly where I need to copy it into memory on my GPU because it's going to correspond to attribute 0, and this next one's going to correspond to attribute 1. That's our limitation. That's not OpenGL's limitation. That's our implementation's limitation of saying that position always has to be at location 0. Your OpenGL code in general would work just fine if I switched these and then switched the corresponding thing in my OpenGL application. It just won't work for our hardware's implementation, so we stick with this limitation. But otherwise, this block of code that I have listed in kind of the main while loop, the main render loop here, only has to be done once. So it doesn't need to be done each time. That could have been moved outside of it. We wouldn't have to call GL disable vertex attribute array and then re-enable it. You wouldn't have to do that at all, to be honest. So the main thing that generally would go in your render loop is usually a call to clear. GL use program also, unless you're changing which shaders are executing, also only really needs to be called once. So that could also go outside the main loop. So you'd have GL clear as part of your loop. You'd have GL draw arrays. That's the final kind of connection with. You've associated all these attributes. Um, let's actually, for a continuous group of vertices, let's issue that drawing routine and say, time to actually draw those buffers that we've created here at the end of the day. You would need to do that each time. And then the call to read from keyboard and mouse events, as well as once the render is drawn, this windowing system's mechanism for saying, hey, it's time to swap our buffers here. Let's now go from front buffer to back buffer and switch them and have them be rotated vice versa. That's how this application does it. Just out of curiosity, if we look at try paint, there's a lot of other things going on here, but it's really just initially initializing the buffers in a different way, right? And then when it comes to the actual render loop here, should be here somewhere. Allocate our VAOs, bind our buffers to those, and then our actual draw loop is a lot cleaner, like it generally should be. Clear the background screen, each frame, draw the arrays of this primitive type given the current buffer and start at location 0 and draw 3 of them. So assume there's going to be 3 vertices getting passed on. Read, wait for mouse and keyboard events, and then do that swapping of buffers. The main difference with the draw paint or the try paint example here is when I do get a keyboard event, I actually do care about what happens. And one of the things that potentially happens is when I get a left mouse button, I can actually change based on X position and Y position of the mouse. I can then update my buffers corresponding to what I want the X, Y location to be of that particular triangle vertex that I'm happening to select there. But the main render loop itself is the same for that example. Let's leave things here for today. Um, Tuesday, I think, will also be helpful. We'll start talking about the rasterization algorithm. I don't expect from this lecture you to become an expert in OpenGL. You're still in really sound footing, just kind of starting from the existing examples. Having the driver open can also help in terms of understanding what we are trying to do when we allocate those VAOs, which are almost entirely just bookkeeping data structures, and then allocating the buffers in which we have to be very specific to where we are putting things in memory, and then connecting that all finally to the draw call at the end of the day, which from our perspective, the draw call is kicking off a big DMA transaction. It's saying, hey, we've allocated these buffers, we have them in the GPU memory because we've copied those triangle data over, the vertex data over, now actually do a draw call. Now actually take those regions of memory, copy them through, and hopefully the end result is what you want it to render at the end of the day. Take a look at those example MP2 applications as well as you work on your labs this week and finish up this week and going into next week. Start with the red triangle, simulate a smaller red triangle if you want to, but then recognize that that is a very nice equilateral, well-formed triangle. Start to simulate also weird triangles as well, but one at a time or two at a time. Don't try to get the whole like Rand triangles or color wheel or other applications to work until you feel pretty good about the triangles that you already have simulating and running on your system there. Let's leave things here, right here for today. And thanks for being accommodating with winter and illness. And I'll see everyone next week on Tuesday.